Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to this lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is Module 1 and particularly in this lecture 1 of Module 1, we will discuss the conductometry. Friends, in order to understand the conductance, we need to understand the dissolution process. And then we will see what Arrhenius theory has to say for the dissociation. Majorly, when we see the chemical reactions or any chemical phenomena, they occur in solutions. In general, if we try to analyze the behavior of solute in solution, we find that the polar solutes are soluble in polar solvents and non-polar solutes are soluble in non-polar solvents. And this is a basic general principle of solubility. Usually we say like dissolves like. Even if you take the example of sodium chloride, it is soluble in water, whereas it is insoluble in carbon tetrachloride. So basically, whenever a substance dissolves in a solvent, it yields either an ionic or a molecular solution. Say in ionic kind of solution, the solute splits into ions, and in case of molecular solution, the solute remains as such in the solution. Look at this chemical reaction. So the solutes can be classified further based on their conductivities in aqueous solution. Look at this table. This classification says it can be of strong electrolyte, weak electrolyte, and non-electrolyte. Now, they can be strong electrolyte, which will give you the solution of high conductivity. They can be weak electrolyte, which will give you solution of low conductivity, or it can be non-conducting electrolyte or non-electrolyte, which will give you the solution of non-conducting or solution which is non-conducting. Now, such behavior is based on solvents, because whenever a solute goes into solvent, it depends on the solvent. Because one solute may be soluble in one solvent, but it may not be soluble in other solvent, and therefore this can be the highly conducting or low conducting or non-conducting behavior is based on the solvents. Apart from this, there is another classification based on the characteristic of solute, and which is not on the solvent. Say we have a true electrolyte or potential electrolyte. So the true electrolyte is the one which is in the ionic character even in the pure liquid state, such as say NaCl or KCl. So they are true electrolytes. However, there are certain potential electrolytes which are not in ionic character in the pure liquid state, say like HCl or acetic acid. They gives you the conducting solution on dissolution in ionic solvent, isn't it? Now, usually we see that there is an increase in molar conductance with the decrease in concentration in particularly dilute solution, and this is true for all electrolytes. Now, this particular fact made Arrhenius to postulate the theory of chemical equilibrium. It is between the undissociated electrolytes and the ions which are resulted from the dissociation. Say for example, if I consider the case of electrolyte AB, it will give you the cation and anion, which accounts for the molar conductivity. Now, there exists an equilibrium between the dissociated ions and electrolyte for weak electrolyte, and particularly it is believed that the strong electrolytes are always in the dissociated state even in the solid state. So this particular case is for weak electrolyte. So this equilibrium is for weak electrolyte. This particular phenomena can be seen even from the various qualitative properties like osmotic pressure, lowering of vapor pressure, or even you can say elevation in boiling point and depression in freezing point, etc, etc, etc. So these are the properties which depends on number of species and not on their nature. So this way, the understanding of dissolution process for understanding the conductance phenomena becomes very important. In this particular discussion of chapter of conductometry, we will discuss all these aspects in due course of time. Now herein, if I want to understand the phenomena of conductance, I need to understand particularly the Ohm's law, because it is regarding the conducting ability of the electrolytic solution. Now the conducting ability of electrolytic solution, it provides a direct proof of existence of ions in solution. The experimental determinations of the conducting properties of electrolytic solutions are very important, because they are used to study the quantitative determination of ions in solution. Not only this, these can be used to determine many physical quantities, say for example solubilities, solubility product of sparingly soluble salt, etc. Similarly, when I take the example of metallic conduction, the electron can flow through metal. Now when electrons from an external battery are forced to flow through metal wire, they displace the electron from the cloud at the point of entry. This can be assumed using Ohm's law. It can be assumed as, say, if across two ends of a conductor a voltage V is applied and a current I, if it flows through it, then the resistance is given by the ratio V upon I. In other words, the current flowing through a conductor is actually directly proportional to the applied potential. That is, this V is proportional to current I, or V is equal to IR. You can see this figure. This animated figure gives you clear idea. This is particularly the potential which is forcing the current, and this is the resistance which is resisting the current to flow from in this direction. This is the best way to understand this phenomena. Now this resistance is the resistance to the particularly current flow in a metal is caused by the vibrations of the metal ions about their lattice positions, because you know that uh, these lattice positions, at lattice position whenever there are atoms present, they are usually vibrating with the energies they available with them. Now such vibrations interfere with the motion of electrons, and consequently they retard the flow of current. Now on increasing the temperature, the thermal motion of metal ion increases obviously, and they offer more and more resistance against the flow of electron, and therefore metal becomes poor conductor with the rise in temperature. Now this resistance, as we have seen, it is nothing but the ratio of applied EMF to the current flowing through the substance called as resistance, and it is given by R is equal to VI upon I. And usually we represent the unit of resistance as volt upon ampere, and it is also called as ohm, and it is denoted by this Greek letter. Now your conductance term is exactly opposite to this resistance. So this conductance is nothing but the reciprocal of resistance, and it is the measure of current carrying capacity of the substance or solution. In this case, in this particular discussion, we will refer to solution, and it is denoted by inverse of resistance. And since it is the inverse of resistance, the unit of conductance is ohm inverse, because the unit of resistance is ohm. It is usually written as mho, or this is ohm inverse, or usually it is called as Siemens. All of these units are same. Now whenever we measure the conductance, we measure the resistance and we take the reciprocal of resistance, and we usually find the observed conductance. Now the observed conductance is not sufficient. we need to see the specific conductance or resistivity. We call it as specific conductance or conductivity, or this specific conductance is derived from the term specific resistance or resistivity. Basically, the resistance of a conductor is directly proportional to its length and it is inversely proportional to the area of cross section of wire. So if I write it down, it will give me the expression like this: R is proportional to length and inversely proportional to cross section area A, and therefore my R is equal to rho into 1 up L upon A. This rho is called as specific resistance or resistivity, and it is defined as the resistance offered by conductor of unit length and unit area of cross section, and the unit of this resistance is ohm meter or ohm centimeter. You can see, you can derive your unit from this particular part, isn't it? So now specific conductance or conductivity is reciprocal of the specific resistance. The reciprocal of specific resistance is called as the specific conductance, and it is denoted by this kappa. And mainly we consider the conductance as the specific conductance, and we take it as the inverse of this resistivity. In SI system, the unit of this specific conductance is ohm inverse meter inverse, or mho per meter, or Siemens per meter. And in CGS system, this unit is mho per centimeter, or Siemens per centimeter, that Siemens per meter that we have seen in SI system. Now, based on this concept of specific conductance, we need to find out what is equivalent conductance and what is molar conductance. Now, why do we need to find out equivalent conductance and molar conductance is because we are dealing with solution, and we need to find out how our solutions are formed, how many gram equivalents are present in solution, and how many gram equivalents are providing the resistance to the solution. And therefore it is very important to find the equivalent in terms of equivalent the conductance in terms of equivalent conductance or molar conductance. So now this equivalent conductance, the charges of solute ions are critical for determining the conductance of solution. Basically, the equivalent conductance can be used to compare the change in conductance due to addition of unit charge on each ion of the solute. Let us take an example of, say, one equivalent mass of an electrolyte in, say, volume V of the solution. It is an arbitrary volume. The equivalent conductivity of an electrolyte may then be defined as the conductance of a volume of a solution containing one equivalent mass of a dissolved substance when it is placed in between two parallel electrodes which are at unit distance apart, and they are large enough to contain between them the whole solution. Is it? So the equivalent conductance is the conductance of a solution containing 1 gram equivalent of an electrolyte, and it is called as an equivalent conductance. It is denoted by lambda, and this is particularly this lambda is the Greek word capital lambda, and subscript to that is equivalent word, and it is given by lambda equivalent is equal to kappa upon C, where this C is the concentration in equivalent per cubic meter. So now if volume of solution containing one equivalent electrolyte is V, then the equivalent conductance is kappa into V. Similarly, the molar conductance can be defined. So the molar conductivity of an electrolyte can be defined as the conductance of a volume of solution containing 1 mole of a dissolved substance when placed between two parallel electrodes which are at unit distance apart. And this particular unit is large enough to contain between them the complete solution. I mean that it gives the conducting power of 1 mole of an electrolyte at any particular concentration, and it can be calculated like this: molar conductance is equal to kappa into V for this particular part, and herein it contains 1 mole of an electrolyte, and this formula is molar conductance is equal to kappa into 1000 upon molarity, and therefore the unit becomes ohm inverse meter square per mole. Whereas if you see the unit of equivalent conductance, it will be kappa upon C, so Siemens per meter upon equivalent per meter cube, so Siemens per equivalent meter square. So Siemens meter square per equivalent is the unit of equivalent conductance, or in this case we can say kappa into V, whereas kappa into 1000 upon normality will be the definition of equivalent conductance. Okay, we can derive the relationship between the equivalent and molar conductance. So if in case of cations or anions, the total charge number of cations or the magnitude of charge number of anions of single molecule of electrolyte, it follows that 1 mole is equivalent to this particular equivalent, nu plus z plus is the charge. So molar conductivity will be kappa upon concentration. So or even equivalent conductance is equal to kappa upon concentration in terms of normality, in terms of molarity in case of molar conductance. So if I substitute here kappa upon nu plus z plus equivalent per mole into molar concentration, so it can be written as this: equivalent conductance is equal to molar conductance upon this nu plus z plus equivalent per mole. It can be derived very easily. So this relationship is very standard, but then majority of the time we discuss the complete description in terms of molar conductivity. Based on this concept, let us understand the numerical. Say in this numerical, what is given: the conductivity of 0.1 molar NaOH solution is say 0.0221 Siemens per centimeter. When an equal volume of 0.1 molar HCl solution is added, the conductivity decreases to 0.0056 Siemens per centimeter. A further addition of HCl solution, the volume of which is equal to that of the first portion added, the conductivity increases to 0.017 Siemens per centimeter. So we need to calculate the molar conductance of NaOH, molar conductance of NaCl, and molar conductivity of HCl. How can we proceed? So we have that molar conductivity of 0.1 molar NaOH solution is, say, we know the formula. Okay, so molar conductivity of NaOH is a kappa upon C. So we substitute the values which are given from here. 0.0221 upon 0.1 moles per dm cube. If I substitute, I get this value, and it comes out to be 221 Siemens centimeter square per mole. Now what is given in the numerical? On adding equal volume of 0.1 molar HCl solution, the total volume becomes double, and the concentration of the salt formed will be 0.05 molar, and therefore the molar conductivity of 0.05 molar NaCl solution will be, say, molar conductivity is equal to kappa upon C, which is equal to 0.0056 Siemens per centimeter upon 0.05 moles per dm cube. If I substitute, I get this 112 Siemens centimeter square per mole. Now on further addition of equal volume of the acid, the solution will become 0.033 molar in NaCl, that is quite obvious, and 0.033 molar in HCl, and because it is the third part of the overall solution, and therefore it is 0.033 molar in NaCl and 0.033 molar in HCl. So the conductivity of this solution will be given by this formula: summation over I into Ci into lambda I. So concentration of NaCl upon molar conductivity of NaCl plus concentration of HCl into molar conductivity of HCl. So on substituting these values, we get this kind of expression, and on solving we get the molar conductance of HCl is equal to 403.15 Siemens centimeter square per mole. So this way we could find out the molar conductance, molar conductivity of NaOH, molar conductivity of NaCl, and molar conductivity of HCl. Similarly, The another example we can see the number of numericals we will solve, it will clear our concept of conductivity. Say for example, the example is given: a conductivity cell filled with 0.1 molar solution of KCl at 25 degrees centigrade has a measured resistance of 24.96 ohms. Calculate the cell constant if the conductivity kappa for 0.1 molar solution of KCl is 0.011639 ohm inverse centimeter inverse, and conductivity water with K is equal to 7.5 into 10 to the power minus 8 ohm inverse centimeter inverse is used to make up the solution. Now, when the cell is filled with 0.01 molar solution of acetic acid, the resistance is 1982 ohms. Calculate the molar conductivity of acetic acid at this concentration. Now, since resistance is equal to resistivity into L upon A, that is rho into K, so K is equal to R upon rho, and that is equal to R into kappa, that is specific conductance. So now if I substitute the values of resistance and the specific conductance, I get this as a cell constant. Now once I get this cell constant, I need to calculate the molar conductivity of acetic acid at this particular concentration. So to calculate the conductivity of 0.01 molar acetic acid solution, so kappa is equal to 1 upon R into K is equal to 1 upon 1982 ohms into this cell constant. If I substitute this, I get this. So conductivity due to acetic acid will be, now this conductivity minus the conductivity of water that has been given for the conductivity water. So I get particularly this. So the molar conductivity of acetic acid at any concentration or at a concentration of 0.1 molar can be calculated using this formula kappa upon C. So if I substitute the value of concentration here in the denominator, we get 14.64 ohm inverse centimeter inverse per mole. Once we understand the meaning of specific conductance, equivalent conductance, molar conductance, then we can apply this analogy in understanding their variations with the concentration. Because as a chemist, we need to deal with the solutions of variable concentrations. And it is very important to understand the variation of specific and equivalent conductance or molar conductance with concentration. So particularly through this figure, we will try to understand. Now the conductance of solution always vary with the concentration. It goes on decreasing on dilution due to decrease in ion per unit volume. Okay, you can see here. We will discuss these terms, what Arrhenius theory says, what de Broglie theory says. Now, when I say that it will go on decreasing on dilution due to decrease in ions per unit volume, therefore the specific conductance kappa, it will also decrease on dilution. It is quite obvious. However, the equivalent conductance will increase on dilution due to increase in volume of solution containing one equivalent of electrolyte. At the point, say in this case, the conductance goes on decreasing, but volume goes on increasing. Say for if you take the case of strong electrolyte, the variation is almost linear. Variation is almost linear. Now, this is for dilute solutions we are talking about. Huh? So this linear variation is seen over here. Now, if you see the case of weak electrolyte, this variation is very rapid. This variation is very rapid at lower concentration than comparatively at higher concentration. Now, why does this happen? Because the molar conductivity is the measure of conducting power of all the ions that are available in 1 mole of the substance. It is therefore obvious that the number of ions that are available for conductance, they increase on dilution. Now for weak electrolyte, the increase in the number of ions has been explained on the basis of Arrhenius theory of electrolytic dissociation. Whereas that for strong electrolyte, it has been explained on the basis of Debye-Hückel-Onsager theory. And therefore it is written in case of straight line, we have written Debye-Hückel-Onsager theory, and for weak electrolyte we have written Arrhenius theory. In short, the increase in the numbers of ions in case of weak electrolyte is due to the increase in the degree of ionization of the electrolyte, which is on dilution. Whereas in case of strong electrolyte, this increase is due to weakening of ion-ion interaction on dilution. Basically, these are the points which are to be noted in the particular case of variation of the specific and equivalent conductance with the concentration. We say that the equivalent conductance of strong electrolyte slightly increases due to dilution. It has a limiting value of lambda at any of this point across this axis, which can be obtained by extrapolating the graph. This is only true for strong electrolyte. This shows that the strong electrolyte are completely ionized at any dilution. It can be clear from this. Now, equivalent conductance for weak electrolyte increases quite sharply. This is what we have seen on dilution, and there is no limiting value, that is lambda, in case of weak electrolyte. You can see here, where does it crosses? You cannot have the crossing at this particular axis, and therefore you cannot have limiting value for weak electrolyte. So now let us have a look at Arrhenius theory of electrolytic dissociation. Consider an electrolyte of this type, AB, and it will give you the equilibrium of this cation and anion of A plus plus B minus of the form AB, and it will be in equilibrium, say for in case of weak electrolyte. So now this equilibrium is characterized by the equilibrium constant K. Obviously, I can write down this equilibrium constant as this particular form. Okay. So now if I say that this alpha is the degree of dissociation, and if I say that this C represents the initial concentration of this weak electrolyte AB, then the concentration of various species are, say, this concentration of cation, which is equal to concentration of anion, is equal to C into alpha, and the concentration of this electrolyte will be C into 1 minus alpha, because alpha is the degree of dissociation. So the concentration of this electrolyte in its form will be C into 1 minus alpha. And therefore, I can write down this equilibrium constant if I substitute the values in case of cation and anion as C alpha, and this electrolyte concentration of electrolyte as C into 1 minus alpha. If I substitute in this particular expression, I get this K is equal to C into alpha into C into alpha upon C into 1 minus alpha. So it will give me C alpha square upon 1 minus alpha. Now, since my degree of dissociation, that is alpha, is much less than 1, it has to be. So we have in this case, this K is equal to C into alpha square, or in this particular case, I can write down this alpha or this expression for alpha in this particular form. So this expression of alpha, that is square root of K upon C, that is equilibrium constant upon concentration, it is known as Oswald dilution law. It is known as Oswald dilution law. Now, according to this law, the degree of dissociation increases as my concentration decreases. Now, as the degree of dissociation is increased, the concentration of ions of, say, A and B, they will also increase, and thus the increase of conductance for weak electrolyte is basically due to the increase in the number of ions on dilution. What the point? Further, what Arrhenius has suggested? Arrhenius has suggested that the degree of dissociation of electrolyte can be calculated using this particular form, that is of equation 6. What does it say? It says that It is the ratio of molar conductivity at concentration C upon molar conductance at infinite dilution. And also the equilibrium constant in terms of molar conductance is given by this particular form, K is equal to C alpha square upon 1 minus alpha. So I can rearrange it. And I can find out this K is equal to C into this lambda C square upon this lambda to the power 0, that is infinite dilution, conductance at infinite dilution, and in bracket the difference of conductance at infinite dilution minus conductance at any concentration C. So now this equation 7 gives me an opportunity to calculate this K. So if I take this C on this side in the denominator, and if I plot a graph of this particular part, particularly lambda C square upon this denominator part versus 1 upon C, because C will come to this side, and if I plot a graph against this particular part versus 1 upon C, I get slope in the form of dissociation constant. Now whatever slope I will get, we will call this slope as dissociation constant, and this way I can find out the dissociation constant using the Arrhenius theory of electrolytic dissociation in case of weak electrolyte. We can solve small numerical based on it. Say for example, the following are the conductivities of chloroacetic acid in aqueous solution at 25 degrees centigrade. So I have this particular data which is described. So concentration is given and molar conductance is given. And if the limiting value for molar conductance for chloroacetic acid is 362 ohm inverse centimeter square per mole, are these values in accord with the Oswald dilution law? It is asked. And if so, calculate K. So I need to first check whether I get a straight line according to the law which we have seen previously. And if it is a straight line, I need to calculate the K. So using this particular data, I can actually take down it in a tabular form. This is a concentration. This is a molar conductance which is given over here. I can find out this particular quantity which we have just now seen. And if I plot this particular quantity with 1 upon C, this is the data which is given. So I get this particular straight line. And since we obtain this straight line, I can say that the Oswald distribution law is followed. And the slope of this line is 0.0015, and therefore I can find out the dissociation constant K in case of this weak electrolyte is chloroacetic acid is 0.0015, and all these values are in accordance to Oswald dilution law. We will stop here in this lecture 1 of module 1. In our next lecture, we will continue our discussion with the experimental measurement of conductance. Thank you.